Welcome everyone. It's a big pleasure for me to introduce our today guest, Dr. Nico Schuster. Nico obtained the PhD last year in Munich, where now he's postdoc working at the Ludwig Maximilian University of Munich. So LMU.
Very nice.
Actually, he's working inside the observatory of Munich in the cosmology group led by Jochen Beller. Is now actually the last days in Munich because from after summer we moved to Marseille in the CPP Institute in Marseille, working with Fabrizio Pisani. He's an expert on the cosmological exploitation of cosmic voids, and also the talk today will be about the cosmic voids. So the floor is yours.
Thank you. So yeah, today I want to talk to you a bit about scale-dependent effects on structure and dynamics of voids, which is a bit technical. I just want to tell you some cool reasons why voids are actually very interesting and what makes them special to use as probes for cosmology. All right, so let's get started. First question is, what actually are voids? And for that, we want to look at the large-scale structure in our universe. For those who are not cosmologists, basically this large-scale structure formed from very small initial fluctuations in density that then evolved as the universe expanded and gravity made structures collapse. But that collapse of structures also created rather empty holes. So first we have the very collapsed structures as knots in our cosmic web, which are just lots of galaxies, clusters, and so on. Then we have one-dimensional structures and two-dimensional structures like filaments and walls. These are really just strings of matter that penetrate the universe, but they're already a bit more underdense than these knots. But what I'm interested in are these rather large and rather empty holes in our universe. So these are the cosmic voids. But of course, we have to define them a bit more properly. And for that, we also want to compare them with galaxies first. So yeah, we know about galaxies that they're quite overdense structures, typically with densities around 100 times or so the mean density of the universe. But in contrast, voids are typically under densities with more or less around 20% of the mean background density of matter in their center. So rather other dense. Another thing about galaxies is they have very complicated dynamics. There's lots of stuff happening, many interactions, supernovae and everything. So the way matter and stars move around the galaxy is very complicated. But in contrast for voids, they have much simpler dynamics, which is one of the things I will show you today. Another thing about galaxies, as I've mentioned, they have supernovae and stuff. So baryonic physics is really relevant. But of course, we also have lots of dark matter in our universe, which only interacts gravitationally. And luckily for voids, we don't really need to care about any impact from baryonic physics. We can just use dark matter only simulations, for example, and compare that with observations. But I'll tell you a bit more about this later. And so yeah, to give you a short outline, at first I'm going to present to you how we define voids and how we identify them. Then next I'm going to introduce the simulation suite that I've used for my work, and then give you a small introductions on voids generally, like their distributions in size and what the typical densities around them look like and how matter moves around them. And then I'm going to tell you a bit more how we can actually connect the density and velocity around voids with linear mass conservation. And in the end, I'm going to finish off with different aspects of baryonic effects around voids. All right, so let's get started. First, how do we find cosmic voids? And for that, we use a void finder called VEID. It's the Void Identification and Examination Toolkit. And it simply defines voids as the regions between any local density maxima, so any local underdensity, and we make no assumption about their general shape, about their size, or about the mean density inside them. So really just anything that's underdense compared to its environment. All right, and for this, VEID implements an enhanced version of a watershed algorithm, which I will explain in a bit, and also can calculate some of the void properties. Namely, we have some radius that's simply the equivalent of a sphere that has a similar volume as the void, the radius of that sphere, as well as a core density, which we will use in a bit. This is simply the minimum density inside the void compared to the mean density of the background universe. So typically you would expect something like 20% of 0.2 here. All right. But how do we find these cosmic voids? The good thing about them is we don't need to do any extra observations. We can use any tracer particle. It can be galaxies in observations. It can be dark matter particles in the simulations, also the halos. And then we can simply create a density field from them. The way we do it is by having these tracer particles here on the left, and we do a Voronoi tessellation, which means we divide our space or volume, be it an observation or simulation, into cells that are closest to each particular particle. So that way we fill our whole simulation box or observation with these different volumes. And from the inverse of that volume, we simply get the density for this region. And that's when the next step starts, namely our watershed algorithm. So in the middle, we see on the left plot, a density field that's represented as height here. So it can be something like the Alps or so. And this watershed algorithm really starts at the lowest density cells. And then we fill up our, in that sense, mountain area with water until it basically sweeps into the next value. That's one boundary of a void, and we continue to do that until our whole simulation box, of course in 3D, is filled. And that you can see in the middle on the right here. We see that the whole mountain area has been plotted, and we see the boundaries of voids, where basically matter swept into the nether valley and defined the boundary. So yeah, this is one example here on the right for a void that we identify then. All these purple cells are really just these individual Voronoi cells and the volumes. So we see it's really not spherical, but rather close to it. And that's why we also have this definition of the radius. And another thing about voids is depending on the density between those. So here, for example, depending on the height of those ridge lines in the middle, we can merge them or not. So you can treat them as isolated voids with no substructure, or rather larger voids that contain multiple subvoids in between them. For the most case, I will focus on isolated voids though, but I'll mention it. All right, so this is how we define our voids. And in my work, I've mostly analyzed them in simulations, for which I use the Magneticum simulations. These are a set of hydrodynamical simulations as well as dark matter only counterpart simulations. They all have a WMAP7 cosmology here on the right. But the more important thing is we have multiple sets of simulations at very different resolutions, which you can see on the bottom here. So we go from 10 to the 10 to around about 10 to the 7 particle masses for cold dark matter, which also means we resolve halos at very different scales, or halos or subhalos in our case, actually. So here we see the subhalo mass function for each of the simulations. Our mid-res, of course, has the highest mass resolution. So we have lots and lots of galaxies in a large box. And then with a high-res and ultra-high-res, we look at halos at much lower masses and go down to around about 10 to the 9 solar masses, actually. So first we have those halo catalogs or subhalo catalogs, and then we identify our voids. And let's look at the simulations first. So here again at redshift 0.3 roundabout, we have our mid-res simulation. Here for the projected cold dark matter density field in the simulation, we have this almost 3 gigaparsec box. And then if we increase our resolution, we arrive at the high-res simulation. We see finer structures in our cosmic web here. And all of this is in a 640 megaparsec box. And lastly, I analyzed a very small simulation of 48 megaparsecs, which is actually not a cosmological volume. So we don't get many voids, we don't get typical voids, but we can still probe their characteristics. And we see quite the similarities between these different resolutions and voids. All right. But here we have the cold dark matter, but what we're mostly interested in is voids identified in halos or subhalos. So from this cold dark matter density field, people apply a halo finder, and surprisingly, it looks similar to projected density field, but of course, emptier regions look a bit more empty because of the halo bias, and we still see lots of nodes and structures here. So as I've mentioned, we have a halo selection at different masses, namely in this rather large box on the left, 10 to the 12 solar masses. And then we go down 1 order of magnitude to 10 to the 11 minimum halo mass, and then around about 10 to the 9. So these are really low mass galaxies, basically. And the last thing that I mentioned is we identify our voids. So you can see some of the projected boundaries here. By our definition, we actually have the whole volume of voids. So I had to apply some cuts in size, but basically every part would be filled with voids. And the rather large voids actually do follow some of the visible structures that we observe. For example, in high res in the middle, can observe it best that the boundaries of voids do typically align with the rather overdense regions and such. So yeah, these are the voids that we analyze. All right, but what are typical properties of voids? So here we have the void size function, which is simply the number of voids at a given size in our simulation or observation. And the most important thing we see here on the left side is that it's actually highly resolution dependent. If we have a higher resolution and lower galaxy masses, we find smaller and smaller voids. So we experience this shift from purple to the red, greenish here. And the same thing if we identify voids in the cold dark matter, we typically have smaller voids already than voids identified in halos at similar tracer densities. But also if we increase the resolution, they shift towards smaller and smaller voids simply because we resolve structures more finely. But one special thing about voids is if we instead look at the void size function of merged voids, as I've mentioned, on large scales, they do align. So round about 45 megaparsecs or so, the void size function of merged voids really becomes independent of the tracer type. We can use galaxies, use halos, subhalos, cold dark matter, baryons. It doesn't matter. We find the same structures on large scales, of course, is expected. All right, another thing about voids is their shape. And we've seen they're not spherical. So we have some ellipticity, that value of 0 would represent perfectly spherical void. But we see that most voids are actually quite close to sphericality. And more importantly, it's totally independent of the tracer type that we're using or the resolution. The distribution always looks the same. It's just shifted by the general number density of voids that we have. All right, and lastly, as I've mentioned, the core density. Here we see it peaks roundabout at 0.2, this value of 20% times the mean density. But again, it's also highly resolution dependent. We see some small shift here. And also for cold dark matter, they typically have not quite as underdense voids. So this is really an effect of the halo bias that we see. All right, but now let's actually focus on the density of voids. So how is matter distributed around them? For this, I present you the density profiles of voids identified in halos, which I will simply refer to as halo voids. Here in case for the mid-res simulation, and we typically average these voids in terms of their size. So we just select voids from given size ranges, for example, here from 5 to 10 megaparsecs, 10 to 15, and so on, and average all of their profiles to see what they look like. And more importantly, if we look at this, we do see that all of these are underdense structures, but only the large voids are really extremely underdense and have a small wall around their boundary. But this actually increases when we go towards smaller and smaller voids. We see that the inner densities do increase, as well as the wall around them, which is something that we call a compensation wall, because it really, some of the wall comes from matter that exited the voids and then forms there. And yeah, many people actually wouldn't consider the smallest bin of 8 megaparsecs to be void, but we still see that they're locally underdense. I mean, their centers are actually round about the mean density of the universe. So these are rather small scale voids in between clusters, but I still consider them void. Yeah, many people don't, but I will show you that they actually share many of the properties, many of the special properties of larger voids. So yeah, they're still voids, basically.
How do you define the center?
The center is, we don't take the particle or the location of the particle with the lowest density, but rather it's volume weighted with the density. So it's a geometrical representation of the center, not just the deepest cell, because that we want, many of those things are assumed sphericality. So we average these profiles in spherical shells around them. So we really want a volumetric representation of the center that factors in the boundaries of the voids, not just the emptiest cell, because that could be anywhere. It could be quite close to the actual center that we define, or it could be right next to the boundary.
So in the smallest b, Do you see resolution effect in this profile?
Yeah, this is exactly this uptick. This uptick that we see, that's another reason why I plot this on purpose, because it does show actually that our estimator is not perfect, because I've mentioned we do spherical shells around the void center. The problem is these particles, they can be located, for example, in the innermost shell, and then the volume of those cells stretches out over many shells. So we have a bias that basically one particle in a very small shell gives us an overestimation of the inner density. So this is why we observe this uptick here and also in the next larger bin, but it's really a resolution effect. So if we increase.
See also the reduction of the number of voids.
True, yeah, we see the peak, most are really rather large and only the very small ones. I mean, many people do consider them spurious, and in observations you would absolutely cut them, but they're still special. And yeah, except for these effects, it's more or less fine in profile. But if I, for example, sample the same void with cold dark matter, we see that it's a clear underdensity. This uptick leaves because if we have enough particles, the disadvantage of using these spherical shells vanishes basically. All right, so here are the profiles of isolated voids, but let's compare them now with merged voids. So the same voids basically correspond to the same colors, but for merged voids we have larger and larger voids. And actually we also observed that round about maybe 30 megaparsecs or so, the density actually starts increasing again in the center of voids, which at first looks weird, but this is really just the substructure of voids, the inner voids inside them that we observe. Like these voids inside larger voids, of course, also have, as we see, large compensation walls. So this adds to the density inside voids. And this difference is really just the boundaries of smaller voids inside them.
But also you see that the smallest bin doesn't change much.
Yeah, the smallest bin basically, I think 6 voids leave that bin. So really small voids are unaffected and only large voids become larger and larger. All right. Next, let's look at the density profiles and actually some alternative methods of stacking. As I've mentioned, people usually do it by size, but here I've depicted them in ellipticity. And we see that basically the smaller the ellipticity is, the more spherical this profile looks like, because we're averaging the structure spherically, and for high ellipticity, the boundary of void basically stretches over multiple shells, as well as maybe a bit into the center of void. So we expect an increase of density in the center and also a broadening of this compensation wall. And lastly, by core density, of course, with increasing core density, the density rises, and they look almost like profiles bin by their size, because there is a strong correlation, but we will notice that the core density can be quite interesting still to look at instead of size. All right, next we want to see how the velocity of cold dark matter and halos actually behaves around voids. So we see this basically in 2 simulations, and on the top I present the velocities of both cold dark matter and halos, and on the bottom, the differences in these velocities. So we do basically observe that on large scales, there is no difference in the velocities of halos and cold dark matter, which is something we expect. Like the velocity should be from GR, it should be independent of the
Radial velocity or tangential velocity?
radial velocity.
Radial velocity.
So yeah, basically we see that large voids, oh sorry, I forgot that. Yeah. Large voids are dominated by an outflow of matter. So they're really large regions, they expand with the universe and matter continues to exit them and they become emptier and emptier. Whereas these small voids, we do observe quite the difference. There's maybe some matter leaving them, but they're actually dominated by the inflow of matter, not towards the void center, but really towards this compensation wall. And this actually also means that some of those voids in the future might be crushed. Simply, if they're too small and structures around them continue to cluster, the void might just vanish. And yeah, it basically also, again, very resolution dependent. If we look at smaller voids, this shifts towards smaller and smaller scales. But yeah, we do see that there is some discrepancy in the velocity of halos and cold dark matter. But again, this is mostly a sampling effect, because if we can sample cold dark matter at much higher particle densities and then get a truer representation of the velocity profile, And more importantly, if we compare those simulations, we see that it breaks the deviations between velocities break down at different scales. So this is really mostly a resolution effect and not some violation of GR or something. All right, but the problem is we can't actually measure the velocity. Like if we look in the sky, we observe the position of a galaxy on the sky and the redshift, but we have no information about the intrinsic velocity of that galaxy because it just gives an attribution to the redshift. And yeah, we have those redshift space distortions simply from the intrinsic velocities of galaxies, and we actually have to model them. So this is where some linear mass conservation comes in. It's simply a linearized version of the mass conservation. And after some math, we can get a connection between well, we have some terms that depend on the cosmology that we're assuming. More importantly, we can connect our density field here, these density profiles, with velocity profiles. So on the left, you see the density profiles actually of individual voids. One example also includes one particle in the center that gives these biased estimation of density inside them. But then if we simply use this equation and assume a tracer bias of 1 for cold dark matter, we compare now the velocity profiles on the right of individual voids with this theoretical prediction. So the more scattered lines are the ones that we actually measure, and the smoother lines are what we actually get from our prediction from linear theory. By simply plugging in these individual density profiles on the left into the equation above, that's what we get. So we see that the individual velocity profiles are quite diverse. They have weird shapes, ups and downs, but surprisingly, or not surprisingly, we recover those extremely weird shapes to a high accuracy. There is some scatter between the measurement, but still very diverse shapes, but we recover them quite nicely. So this is done for cold dark matter, but actually we can do the same thing for halo-defined voids. In that case, we can't assume a bias of 1, but simply we fit this because it's mostly just an amplitude. And as we've seen before, in both simulations, it recovers very diverse profiles to extremely high accuracy. So this is for voids typically in ranges 23 to 50 and also 20 to 30 megaparsecs. So it's large voids, and we see that, yeah, these large voids have linear dynamics on large scales, which is good. But actually, at some point, we're going to push this a bit. But first, let's now look at the average profiles. Oh. Sorry, yeah. So again, we do the same void bins that we've seen the velocity profiles before, but now we actually compare our measurements with our prediction from linear theory, and we have the averaged void bias parameters here. And we do see, again, we nicely recover these profiles, and we do see some discrepancies on small voids on small scales, but we find a similar agreement between these. At different sizes, for example, a 22 megaparsec bin has same level of mismatch between our data and the model than, for example, the bin of 12 megaparsecs in our high-res simulation. So this already hints that these deviations, again, are mostly a resolution effect and not truly an onset of some nonlinear terms. But yeah, resolution and a sampling effect. And to actually try this at smaller scales, I used this ultra high-res simulation. So as I've mentioned, it's a 48 megaparsec box with 350 roundabout voids that we find in the halos. And yeah, first let's look at the stack profiles. Again, at very small resolution, small scales, they still look like the typical profiles of voids that we see. We do observe the outflow of matter and the inflow of matter. And here, by comparing the data with our model, there seems to be no disagreement. But of course, with 350 voids, error bars are very large, so I would not trust this, to be honest. But luckily, again, let's look at individual voids. And as we've seen before, it basically works. Again, we have very diverse shapes. We recover our profiles. But most importantly, this actually works for very small voids. So the one depicted in red here, it has a size of 1.4 megaparsecs. So really, this shows us, even though the shapes are diverse and there are some sampling effects, we can nicely recover the velocity and the dynamics of matter around voids, even down to scales of around about 1 megaparsec. So this really shows that voids still behave linearly at scales that we typically would consider to be nonlinear in physics. So yeah, that's one great thing about voids, and that can actually help us in using this to work on redshift space distortions at much smaller scales than we're currently using. So basically, we might not have to cut as many voids in observations as we currently do, because we can actually model this quite nicely. All right, but another thing is that always ruins observations, baryonic effects. So I've mentioned before, we have different resolutions and simulations, but in our mid-res simulation, I didn't find any deviations, simply because the resolution was not enough to find any baryonic effects. So from here on, I will only present results from the high-res hydrodynamical simulations, and I compared this with the dark matter only counterpart. And yeah, there we find some small effects, all of that here now at redshift 0.25, but of course at redshift 0, we don't expect any large differences. If we again identify our halos between the hydrodynamical and the dark matter only simulation, we find now a slightly different numbers of halos between these simulations at a fixed mass cut. So that in turn also gives us different voids already, because at different tracer densities we've seen before that void profiles and distributions change. To counteract this, we also, and to imitate observations, we fix the halo density simply to the one that has less halos in at the fixed mass cuts. And then we again identify voids in these matched halo density catalogs and analyze them and compare them now to see what we get. All right. First, again, I want to show you the projected halo density and some of the voids we identify within them. This is from the hydro simulation. But how does this look like at same conditions with the dark matter only counterpart? It looks, some of the structures, because here, look more or less similar as we expect. But more importantly, we see that voids typically do not match between simulations. We find some match, for example, those depicted here in red, but most do not match. So this really is just to show that we can't compare individual voids between simulation, but we should rather focus on their statistics and see if we find any deviations. The color code is basically the depth within the slide, within the projection. It's not terribly important, but really just these overlapping voids that we see sometimes. There it's important that the color code shows that they're in projection only overlap.
But he used the matched halos in dark matter only and full light.
This was for simple mass cuts. But even at matched halo catalogs, the voids themselves do not align perfectly. So yeah, now we need to look at statistics. And again, we want to look at the void size function first. Another thing I did here was actually identify voids in baryons as well, instead of only the cold dark matter, as well as the cold dark matter particles from our dark matter only simulations. And basically we see that there may be slight deviations of matter voids. We have a slightly higher number of voids identified in baryons, but more importantly, voids identified in cold dark matter, you can use any dark matter only simulation. The feedback from baryons and cold dark matter does not affect the statistics of these voids. And another thing that we look at here is for halo defined voids again. And once more, we see that without, can't see it properly, but in the not matched catalogs, simply with the mass cut, we observe slightly higher number of small voids in our hydro simulation. And after matching, this drops down and voids are almost alike. There are small deviations, but still on very small scales. So from this, we should be able to use actually dark matter only simulations for the void size function and the predictions, and don't need any baryonic physics because it's rather unaffected. But one distribution that can be affected actually is the core density of voids. So again, here for voids identified in cold dark matter and baryons, and as before, the voids identified in cold dark matter, they don't differ between our dark matter only simulation and the hydro simulation. But we do observe, it should be a small line here in green. We do observe a shift for voids identified in baryons towards much higher core densities. So we already see here that voids identified in baryons are not quite as empty as voids identified in the cold dark matter, which we will actually see a bit more later on. And again, here, for the voids identified in halos, we find that voids are slightly less dense in their centers in the hydro simulations, but these are just very underdense voids, so very few numbers, and this is a deviation between the simulations that we can actually ignore. If these voids are too few in numbers to actually have a significant effect on these distributions. All right, now let's again look at the density profiles, but this time for voids identified both in baryons and in cold dark matter, and we compare the densities around them. So yeah, I've mentioned here the density profiles of cold dark matter voids. I don't depict them here because between simulations they differ. We can use dark matter only simulations for these profiles, but for of course voids identified in baryons, we do need those simulations, and we see that profiles are mostly the same, except the compensation wall has a slight change, as well as some small change in the densities of baryons within the smallest set of voids. But otherwise, mostly they have the same statistics. But if we again depict them in core density, this is where our effects show up, really. So we see the voids with the smallest core density, truest voids in that sense, they are still unaffected. Voids between baryons and cold dark matter behave the same. But if we go towards higher and higher core densities, so basically voids in more and more overdense environments, we see that deviations start popping up and become quite large for the most overdense voids, which really shows that baryonic effects are more relevant depending on the density that we look at instead of the size that we look at. But yeah, I'll get to that in a bit as well. But more importantly for observations, we want to actually look at voids identified in the halos again. And we see with the fixed mass cut, voids, the largest and smallest set of voids, experience differences in the densities. So this would have to be accounted for slightly, even though the effect is small. But to mimic observations, we perform these matched halo density catalogs, and the deviations that we find do decrease a bit. So there's still very small effects on the largest set of voids and the smallest set of voids, which still might be due to small changes in the number densities in these bins. But even then, if we take this for full granted, the effect is basically on the order of 0.02 times the mean density. So while it's there, we don't really have to take into account much of this effect. There's only small deviations in the densities, and only for the smallest set of voids that aren't actually used in cosmology so far. So yeah, matching the halo densities actually reduces any potential effects we do find in halo-defined voids. And we can push this once more by binning in core density, where we actually see that these effects still remain. Again, we see that matching halo densities reduces effects between our simulations, but when we depict voids by their environment, their profiles do change significantly. It's less than between baryon and cold dark matter defined voids, but when binning voids in core density, this is something that really needs to be taken into account when we were to do this in observations. All right, lastly on these halo-defined voids, I want to show you again the velocity between simulations. And as we've seen in the density profiles, there are some small changes for the largest set and smallest set of voids on the left. But after matching densities, the velocities do agree perfectly. Which is also a good thing because I've tested our predictions on the velocity for voids in our hydrosim. But actually, I could have tested this in the dark matter only simulation as well, and it doesn't make a difference. All right, but again, if we depict now in core density, we do observe slightly higher deviations, but mostly they're negligible. And actually, this is also, if we look at velocity profiles in non-radial bins, there's a whole lot of different trouble that will show up with the different estimators that you can use for these profiles. But there's more in a paper of mine that you can check out. I don't want to go into the messy details of estimators, but yeah, if you estimate velocity around voids, it's really important how you estimate it. All right. Now the last thing that I want to present to you is the density of cold dark matter and baryons around the same voids, namely voids identified in halos. We've done this for each individual void and then stacked these differences in baryon and cold dark matter densities around them, which doesn't make any effect on the magnitude that we find. We could simply do the difference between those two and get the same. But we would have larger error bars, because here we see some of those profiles basically overlap within the error bars. But if we do this around individual voids and differences in densities between cold dark matter and baryons really happen on an individual basis and would have to be accounted for on the basis of individual voids, we get smaller error bars, which is actually what we find. So yeah, what do we see here basically? We see that the smaller and smaller voids are, the larger deviations between the densities of baryons and cold dark matter are, and we find an overabundance of baryons inside voids, and a slightly smaller number of baryons in the compensation walls here, which can be interesting, and that definitely needs to be taken account for if we were to study voids and recleansing. But more importantly, this might also be regions where we could look for the missing baryons. This is still one of the open problems in cosmology. We don't observe all baryons that we kind of need. And so yeah, maybe we should look into small voids. They really have a significant overabundance of baryons compared to the cold dark matter. And this can also help us to pinpoint maximum differences between those simulations. Because if we see deviations between baryon and cold dark matter densities on that order, I'd expect the densities between halos to be much less, or at most of this order. All right. And lastly, here we actually also looked at this at a different mask cut, namely the one we used in our mid-res simulation, to see if it was a resolution effect, why we didn't see any baryon effect, or if it was really the minimum halo mass. And we see that in the high-res simulation, we still observe deviations between baryon and cold dark matter densities at the mask cut that we've previously used in the larger simulation box. So really the resolution was not enough. And that needs to be something that should be tested further. So this hints that we should actually look at even higher resolutions to see if that's the end of differences between densities. So yeah, resolution of mid-res was not high enough to find any baryonic effects. Our high-res resolution was enough to pinpoint some, but now I'm going to present to you something from, actually in 2 slides, something that probes this even higher. And again, here I've depicted these differences in core density bins instead. They look, again, very similar to the ones between void size bins, but once more deviations become higher and higher than in void size bins. So this really pinpoints that the core density, the inner density of voids, really determines the structure of matter around them, not the size themselves. And this is really where the strongest deviations show up. All right, I've tested this also with other void properties that's in the paper, but core density really is what determines the strength of baryonic effects. But yeah, now let's lastly look at the density profiles between simulations. So this again on the left side is for high-res simulation and the right side for ultra high-res. As before in the ultra high-res simulation, we have very few voids and they have slightly higher densities even. But we do see that the differences actually vanish at similar scales. So here we've depicted the void profiles actually in co-moving scales instead of centering all the same structures at the same point. And we see that basically around about 10 megaparsecs from the void center in both cases, we do not find any significant deviations between densities of baryons and cold dark matter. So this gives us really a nice limit there. And we do find in the ultra high-res simulation slightly higher densities or differences in density between baryons and cold dark matter. But while it's not depicted here, I've managed to push the high-res simulation with an even smaller bin, and I found a similar agreement at similar scales between the densities. So really, we can trust our results from the high-res simulation, because even at much better resolution, we still find the same order of magnitude. it's different voids, but it's still the same order of magnitude for deviations between them. So that's a good thing. At least we find some upper limit, but of course it could still be studied for much smaller voids in more detail. All right. And yeah, to end this, I want to show you a bit more on the ultra high risk simulation, namely some individual voids. Again, these are individual voids, and we calculate the densities of baryons and contact matter around them. And well, it looks like there's some effects, but actually in this very small simulation, I could sample the profiles to a much higher degree. So let's do that. Here I've used, I think, 1,000 shells. So each shell size is at most 48 kiloparsecs. So this is really small scale void profile. And basically we see that in dashed lines, the contact matter still behaves as we find in the average statistics of voids, namely an overabundance of contact matter compared to the dotted lines of baryons at overdense regions. And if we look at underdensities, we find an overabundance of baryons inside them. But more importantly, this is not just true for typical void profiles, but really for any local overdensity or underdensity. So to showcase this, for example, in the purple curve here on the right, we see that we have some structures that are all above the mean density of the universe, but still we observe that the clustered regions experience peaks in the contact matter, whereas the locally underdense regions here have a much more smoothed out density of baryons. And similarly on red, we see that even for overdensities that are below the mean density, contact matter still clusters much more strongly, whereas baryons are distributed much smoother. So this really shows that what we find in the statistics of average voids and many voids still is true for individual voids in any local underdensity, really. So this is something that tells us a lot about the general formation about underdensities and the interaction of baryons versus contact matter. And it does make sense because we know that contact matter only interacts gravitationally. So this can really cluster a lot. Whereas baryons in the galaxy, for example, they can get pushed out as well. We have supernovae, we have AGN feedback, and all of this can really push out galaxies outside of, well, can push baryons outside of the galaxies. And some of them end up in rather underdense regions around them. And we see a similar thing, I don't depict here, in the velocity profiles, namely individual void profiles. The contact matter has a much more scattered velocity profiles, whereas the velocity profile of baryons is quite smooth, simply because due to more frequent interactions, there's a much more coherent flow of matter, whereas contact matter just gets spilled out or behaves more chaotically. So this really, you can explain these differences in densities by simple assumptions about physics, namely just any interaction can push out matter, whereas contact matter can only cluster. And we see that underdensities are quite special in terms of baryons. So really, we should look here for some of them. All right, so now let's come to the conclusions. I've shown you different properties about voids, namely that, for example, merged voids, they typically have shallower density profiles than their isolated counterparts because they have the substructure and the walls of smaller voids inside them. And more importantly, we find that the void size functions, so the number of voids of a given size, converges on large scales, becomes independent of the tracer type we're using for the void identification and independent of the resolution that we're looking at. Next, we see that the contact matter particles and the halos basically move at the same speed around the same voids. We do see that large voids are typically dominated by the outflow of matter as the universe expands, whereas small voids are dominated by an inflow of matter towards the boundary of voids. We see that both individual and average voids accurately obey our linear mass conservation, which connects the density of voids with the velocity of matter around them. And this actually holds down to scales of order 1 megaparsec, or maybe even further if we could check. And basically we see that voids have much simpler dynamics than galaxies, even similar scales. And lastly, if you want to know more on, for example, weighting profiles by the halo mass, how to estimate the velocities of voids in different ways, as well as some sampling effects in these profiles. You can check out this paper. And as for baryonic effects on voids, we see that cold dark matter defined voids, which are relevant for weak lensing studies, are basically similar between any hydra and dark matter only simulations. So we don't need to run much more expensive simulations for weak lensing studies on voids. And even for halo defined voids, we found the same thing. Like baryonic physics has a small effect, but if we match densities, it still reduces. So yeah, and lastly, we find baryonic matter is distributed much more evenly around voids or generally under densities compared to the cold dark matter, which is much more clustered. So to summarize this, basically we see that voids behave extremely linear at small scales, and at small scales baryons are not relevant. And all of this can really help and improve current observation of voids. We can push this down to much smaller levels that we're currently using. And yeah, let's hope we can get some cool science with this in the future. Thank you for letting me speak.
Thank you very much, Nico, for your question. Now, Stefano, please.
Yes, a couple of questions. One is how many of these flaws or prediction can be validated with observation data set? Any rules or limitation using observed points for making such comparison?
So I mean,
just completed the question, sorry. And is any dependence of the quantity that you show on some environment, meaning distribution of cluster nearby, filaments, pancakes, or walls?
First, regarding the observations, so yeah, to be honest, it's tough. Like the velocity profiles, we could theoretically do that with every. I mean, I think there's some methods of estimating galaxy velocities for nearby objects, so we could do it in principle there. I think there's been some measurements, but really for cosmic voids on large scales, it's tough. I mean, we can only guess that as well, but really it should be tested for nearby voids, and if it holds around there, the measured density and measure velocity with the prediction, then it should also hold for voids at earlier times. I haven't mentioned it in the talk, but actually I tested these linear theory predictions between redshift 0 and redshift 4. It doesn't make any difference. And I've tested it in different cosmologies. For example, matter content in our universe, omega m of 0.15 to 0.43, and even that doesn't happen. So it's really, at least from the simulations, it's time and cosmology independent. But yeah, to verify it, that can pose a challenge. The other question was environment. I haven't looked at environmental dependence in terms of filaments or something, but I've looked at the environmental dependence in terms of the average densities of voids instead of the minimal density, and they behave quite similarly. So the average density does correlate somewhat with minimum density, and they both show stronger baryonic effects, for example, than bins of void size. But the strongest determination really is the core density, so the inner density. It seems to not depend as much on the global environment. But of course, it might be interesting to study this, for example, depending on identifying voids in different types of galaxies. Then that might change if they're in different stages of evolution, there might be different feedback. So there could still be potentially some deviations between the densities, baryons and cold dark matter, that differ depending on the type of galaxies, for example.
So just a couple of things. So in this case, you showed voids identified using the halo color. And you did the comparison with CDM only and light flow simulation. So using only the hydro simulation, have you identified voids using the galaxies in the hydrodynamical simulation and compared, for example, in the same hydrodynamical simulation, voids in halo catalog and in the galaxy catalog?
So we're using the subhalos instead of the normal halos. So by assumption, they should be at least closer proxies to the galaxies. And I've tested the same thing for halo identified voids or subhalo identified voids. And the comparisons between hydrodynamical and dark matter only simulations still hold true. The density profiles slightly changed whether I use subhalos or halos, but only small deviations of the densities within voids. But generally between the simulations, they don't.
But you haven't used the
Sala mask
galaxy
we haven't looked at.
Okay. And the other thing, have you tried, are you planning to use the light cone, for example, for the Magneticum simulation, and then the galaxy catalog in such a way that you can build up effective catalog and properties that you can compare with observations?
I'm not sure if there is a light cone on the simulation, but we haven't.
There is a light.
Oh, even for the high res?
Yeah.
Ah, okay, then I should test that.
Okay.
So kind of it can be used for mesh-based grid-based code.
You can do it grid-based as well, but I prefer the version. Let's go back of Lead because I want to make as few assumptions as possible that I can. Like grid-based, what's the grid size that you want to average at, and so I don't see much of an advantage there. I prefer, most simple approach, no assumptions about shape, size. Like I've used the minimum void radius of I think 1 kiloparsecs or so, and usually people cut voids at I don't know 10 megaparsecs or so. So yeah, I think with grid-based void finders, some of the assumptions might change, but that might also be because of averaging of the grid. And of course, this fine tuning, like in the ultra high res simulations where I look at 1 megaparsec voids, that definitely needs a very different grid than the high res simulations with like 50 megaparsec voids. So I haven't investigated the grid-based method. I expect most changes if you have a finely enough grid or a well enough definition of the center to still hold in those cases.
You haven't tried MHD, right?
Sorry?
You did not try any MHD, so you only use hydro.
Yeah, only hydro. I have some other projects that are relevant to this, but yeah, otherwise it's mostly the hydro simulation.
So along the previous question by Carlo, like even simulation. So when you talk about the halo voids, you mean that you are using all halos beyond a given mass or a given. So did you try instead to check the mass of the halos, to try with different bias tracers to identify the halos? Let's see. Your conclusions also depends on the mass of the halos that you use to define the voids.
So yeah, I haven't plotted it in the talk, but I've also tested, for example, mascots of 10 to the 13, 10 to the 14. Still works. The bias changes, that's expected though, but it still holds. Like for basically every order of 10, 10 to the 10, 10 to the 10 I haven't tested because the resolution here is not enough. But otherwise I've tested various mascots and at least subhalos and
so I mean
halos.
You rerun with selecting different with different mass tracers. And you get, for example, the dynamics is still linear, but whatever.
Dynamics still work. The profiles they do change because of the scale change. Baryonic effects, I've only tried these two different mascots, 10 to 11 and 12, because above, like we see in mid-res, we don't get, it's not resolved to pinpoint baryonic effects. And in high-res, in red here, we see that at 10 to the 12, we still have enough halos, but 10 to the 13, it breaks down. Like we don't have, I think here we have at 10 to the 12, round about 5,000 voids, whereas at 10 to the 11 mascot, we have 35,000 voids. So we can't push this sadly much more.
And then maybe minor, I didn't understand when you say merged voids. So what do you mean exactly? So how do you merge? Which kind?
So there's a theoretical value somewhere that somewhere that says we should use 0.2 merging, which is I'm not 100% sure where it comes from, but yeah, we can predict that it should be 0.2 merging. I've tested that and too resolution dependent again. So in our case, I used a merging threshold of infinite, right? Which basically means we find one large void, that is the whole simulation box, and then we have different levels of subvoids. So this is really the most basic assumption of our merging. I just want to merge everything, because if I pick a specific number, then it's again too resolution dependent, which is not
So
great.
when you say merge, you mean you are merging subvoids in a single. So when you mention merged voids, it means that you have subvoids that are merged in a single.
So basically, the number of voids doesn't change. Like the number of voids is simply given by the number of local minima. But then let's go back to this one. Then really just these get merged, and everything gets merged. And then we have different levels of, depending on the height of this wall, we have different levels of substructure. But in the end, everything is one void, which is of course not the one void we're interested in.
Before I have one question. So do you think that your conclusion about the baryonic effect can be dependent on the specific modeling that you use for the gas physics in the magnetic simulation? So
in principle, yes, but luckily the Magneticum simulations actually have a bit too strong feedback. So at least the conclusion of that we don't need baryonic physics for halo-defined void statistics, I'd expect that to still hold true in different gas feedback parameters or something. But the conclusion of the baryonic content inside voids, that could change slightly. I still think, I would say it's a true statement that local underdensities contain more baryons, because like the physics tells me something can be pushed out, whereas cold dark matter can't really. But the absolute magnitude of how much baryonic content differs, that should be dependent on the properties that you implement on how strong the feedback is.
if there are no more questions, let me thank again Nico. We will be here in around this day.
So I'll be around today and tomorrow. I think, what's my office again?
Yes.
3 and 8, so yeah, if you want to come by for a chat,
Oh,
great.
okay.
Otherwise, you can also drop me an email and we can have a chat.
Okay.
Thank you.
Very much. Bye.
I just had a question. So if I want to use this for my